Assalamualaikum and hi. For this video, I will discuss about the introduction on the control systems. So what is a control system? So I will explain briefly in details, including the terminologies and the concept behind the very basics of the control system structure. So let's take a look.
Right. In this chapter, we will cover introduction about the control systems, and then the terminologies of the control system that we always use in these subjects. And afterwards, you will use for your design work or any as your knowledge. Okay. And also the basic components of the control systems, and lastly about the types of control systems. So we have a closed loop and the open loop type of control systems. Very basic part in the control systems. So by the end of the lessons, you should be know how to identify the control terminologies, how to use it properly, and understand the meaning behind the terminologies, and describe the control configuration or the control system structures, and explain the difference and similarities between the types of the control systems. Alright, so what is a control system is all about? Okay, before we go to the terminologies, okay, the control system is really the systems, okay, any systems or machines or something that move with the controller. Okay, so when the system with the controllers and the plant or the system or the device that move because of the controllers, so we call that the whole thing, we call that control systems. The environment is a control system. Okay, so in the control systems, we usually use the control variables, manipulated variables. They have variables inside the controllers, the control structures. Okay, and then we have a plant in the control structures. We have a process in the control structures. We also have actuators, which is process and actuators is actually part of the plant's structures. Okay, and we have a systems, so we can say that fan systems, we can say that refrigerator systems, we can say that washing machine systems. Okay, and then that system have a disturbance. Okay, every systems without the smart controller or without the closed loop controllers, they have a disturbance that bother the control inputs. Okay, and then we have a type of control system: open loop without feedback, and closed loop that we always use in automatic controller, or we want to design a smart systems. We have a closed loop control system with a feedback. Right, so as I mentioned previously, so the control environment, we can say that the system with the control environments, we can say that the whole thing is a control systems, which is basically we have a input, and lastly we have a outputs. Okay, so the inputs is our objective. Okay, the objective of the system means that you want to change the, for example, you want to change the speed of the fans. So the objective is the button of the speed. We have what commonly we have stop 1 2 3 on the speed, and we have a stop, we have a on. Okay, so that one is the input as an objective, and then the results is the air. So for the open loop control systems, okay, OLCS, so LCS, you always with the OLCS system, especially for the simple appliance, okay, like tools like a grinder, or you have a cutter. Okay, that one is something that we don't need feedback. It's different to the closed loop control, CLCS. So CLCS, they have a feedback that usually we use the sensors or transducers. So the plant will give the output that measured by the sensors. So the sensors will give a feedback to the input reference. Then we calculate that by deducting the reference to with the feedback, okay, and then we get the error. So the error will use by the controllers as an input, okay, different to the open loop control system. They use the reference as an input, but for the closed loop control, they cater or they get input, they feed error as their input, okay, then the controller will regulate and calculate what it should be for the actuators or the devices input to trigger the plant. Okay, that's the whole thing I can say about the CLCS. All right, so here a bit detail about the closed loop control. We sometimes combine both open and closed loop control in one complete structure of the system, because sometimes some part of the controllers, some part of the system no need to use the closed loop or feedback response, okay. Another part needs some intelligence to make good control. When we say about control system, okay, control system that we design, basically we design part by part, because in the complete whole system they have several structures, okay, like a robot joint, for example. Okay, robot joints, every each joint we need to have one closed loop joint control, okay. We don't design the whole joint for one single control systems. That's going to be a very complex control system design. I don't say we cannot, because they have some research. That one is more on advanced control system design. Okay, they call that a multiple inputs, multiple outputs control, or you can search multiple input, single output control systems. So for your case, it's just a CISO, single input and single output control systems. Okay, so this is different between OLCS and CLCS, which is obviously OLCS is for simple systems, because closed loop control have a closed loop or feedback elements compared to OLCS. All right. This is an example. Let's say we go to the steering car. Okay, so like a steering car, they have a desired from the user. Okay, so desired from the users, and then actual situation, this is actual direction. Okay, so for the example, okay, we just focus to design the controllers on the direction of the automotive systems, like a car, steering car here. Okay, so in the car itself, they have several controllers, maybe on engine controllers, maybe on braking controllers, maybe on a civilian smart controllers. So here we just focus on direction controllers. Okay, the desired input will be the course of the travels, okay, from the users, the desired path, desired directions. So desired directions will be deducted with the sensors of the actual course travel, and then we get the error of the signal, indicates the error. So that signal we send to the controllers. Okay, For this case, the driver is the controllers. Okay, so that car will control the actual output that's going to be like what the human drivers want. Okay, so then the drivers will control the actuators in the steering mechanism. So they consider in the design is a disturbance. Okay, maybe disturbance come from noise, it's come from vibrations. That thing also we acquired from the sensors. So disturbance also get from the sensors, not only the feedback. All right. So how about the antenna satellite systems? Okay, the same thing. Okay, you need to identify which one is input, okay, which one is feedback, okay, who's the plant, so what is the output that they desired, okay, so then you can design the controllers. Okay, so here I want to highlight is the when we calculate the feedback, so we need to calculate the same units for these systems. Okay, we need to take the voltage input because we want to minus with the voltage output. Okay, so potentiometers can convert from the mechanical rotational into the voltage. So same goes to sensor for the azimuth rotational will convert the rotational mechanical into the voltage, because we want to find the error tracking. That error tracking we need to send to the controllers. So that's the main point I want to highlight when we design the control systems. How about the airplanes? Okay, so airplanes also the same thing we do. Okay, we need to find which one is the sensors, which one is the controllers of the airplane. Okay, so what is the inputs? For this case is from the drivers, like a car just now. Okay, and then they have a steering pedal or something inside, and then give the motion movement of the airplanes on its wings. Okay, the wing is moving a bit, like they have kind of swing a bit on the on its wing, right? So that one is a controller of the airplanes. For this case, okay, we want to control the attitude or the posture of the airplanes on the air. Okay, to get the posture feedback, we use the gyro sensors. So the gyro sensor inside the airplanes become the feedback, okay, for us to design the controllers. Okay, let's say we have a to design a roll, angle, attitude controller. So here is the example of the flow diagram that we can draw. Okay, we have a pilot control, and the pilot control have voltage input, and from the gyro feedback we just take the roll angle only. So this should be here is a roll angle is a X, so gyro voltage for the Vx. Okay, because the X exists here. Okay, just for the roll. Okay, so this one is controller for just for the rolls. Okay, for the yaw and pitch you need to design another control structures. Right, so you need to understand which one is the positioner of these airplanes, and this aircraft dynamics and integrated is actually the plant. Okay, this one is a plant. Okay, you get the equation, or you get the model structures of the airplanes, so easy for you to simulate this airplane motion control to get the control design, because these controllers you will reprogram. Okay, you will reprogram to the actual controller inside the airplanes. So that's how we design the control systems. So after we get the simulation, the good simulations, we get the good results, and then we abandon the algorithm inside the controllers, and we try again. Because in practice, if you ask me, in practice we retune the controllers, but at least we have a base. Okay, we have a base in simulations where we want to start, and we can avoid any destructive, any damage, okay, on the hardware. Okay, we can try first in simulations. All I can say is with the minimum risk, if compare you directly design the algorithm inside the hardware systems. Okay,
That's all for this video. So you can wrap your information that you get in this video according to the list given behind me. Okay, so I think for the next video I will explain about the how to model the control systems, and I hope you still with the channels, subscribe, like and share. Thank you very much.